All right, let's get right into it. We're about to question something so fundamental to mathematics that most of us just assume it's true. It's one of those questions that, once you really think about it, kind of shakes the foundation of what we even mean by truth.
So look at this question. Is every mathematical statement either true or false? I mean, on the surface, it seems kind of obvious, right? 2 plus 2 equals 4 is true. 2 plus 2 equals 5 is false. Case closed. But what if it's not that simple? What if a bunch of brilliant, rebellious mathematicians came along and said, nope, not always. What if there's a third option, a sort of limbo, where a statement is neither true nor false, but just undecided?
To get why this was such a big deal, we have to go back in time. Let's visit the established empire, the world of classical mathematics, right around the turn of the 20th century. This was a place of absolute certainty, built on rules that seemed totally unshakable. And the number one law of this land was the law of the excluded middle. And look, it feels completely natural. A number is either odd or it's not. A statement is either correct or its opposite is correct. There's no gray area, no maybe, no middle ground. It's the ultimate black and white, this or that rule of logic. Now for them, this wasn't just some convenient shortcut, it was a core belief. Classical mathematicians pretty much saw themselves as explorers. They believed that mathematical truths were just out there, floating around in some perfect, ideal universe, just waiting for a smart person to stumble upon them. Truth was absolute, and it had nothing to do with us humans. And right into this perfect world of certainty walks our guy, the Dutch mathematician L.E.J. Brouwer. He took a long, hard look at this beautiful kingdom, at its most sacred law, and had the nerve to ask, hey, what if you're all wrong? And this wasn't some overnight revolution. It was a slow burn. Brouwer started publishing his really radical ideas way back in 1919, and other thinkers like Arend Heyting came along later to help give them a more formal structure. This was a huge philosophical shift, and it took decades to really build up steam. This quote right here, this is the heart of it all. For Brouwer, mathematical truth wasn't something you find like an explorer. No, it's something you build, something you make right here in your mind through a process he called a construction. You know, think of it like baking a cake. To a classical mathematician, the idea of a perfect, flawless cake exists somewhere out there, even if nobody has the recipe. But for an intuitionist, a cake only truly exists if you have a working, step-by-step recipe to actually make it. If you can't produce the recipe, you can't claim the cake exists. It's that direct and, yeah, that revolutionary. Okay, but if truth needs a recipe, if it needs a construction, that leads to a pretty shocking conclusion. It means that the old kingdom's most sacred law, the law of the excluded middle, has got to go. It has to be broken. And here's where they clash. The classical view says a statement like, it's either raining or it's not raining, is just obviously true, period. The intuitionist says, hold on. To claim that, you have to either show me a proof that it's raining or show me a proof that it's not raining. You need a construction. This is why they reject a really common tool called proof by contradiction to prove something exists. You can't just prove that a world without your cake leads to some logical mess. For the intuitionist, you have to actually show me the recipe for the cake itself. The real battleground for all this was infinity. I mean, for a small, finite set, sure, you can check every single item. But for an infinite set, like all the whole numbers, you can't check every single one. So how can you possibly say a statement about all of them is definitely true or definitely false until you have a concrete method, a construction that proves it one way or the other? Until you have that, its truth value is just undecided.
But here's the cool part. Brouwer's goal wasn't just to tear down the old ways. By kicking out that one core assumption, he and his followers basically cleared the ground to build entirely new worlds of mathematics, ones that operate by a totally different set of rules.
And the result was just incredible. Brouwer's ideas set off this chain reaction of creativity. Whole new fields started popping up, all based on this constructive idea. Things like intuitionistic mathematics, constructive set theory, you name it. This wasn't just some tiny little tweak to the old system, it was a whole new branch of mathematics growing from the ground up. And let's be super clear here. This new constructive mathematics is totally rigorous and self-consistent. It's like a parallel universe of math that works perfectly fine without ever needing to assume that every statement has to be either true or false. So at this point, you might be thinking, okay, this is a fascinating but very abstract 100-year-old debate. But this is where the story takes this amazing, unexpected turn. Brouwer's philosophical rebellion has a powerful, powerful echo in the digital world we're all living in right now.
Okay, so check this out. Let's connect the dots. A constructive proof is a recipe, right? A step-by-step procedure. Well, what else is a step-by-step procedure? A computer program. And here's the mind-blowing insight, what's known as the Curry-Howard correspondence. These two things aren't just kind of similar, they are structurally the exact same thing. A constructive proof is an algorithm.
Just let that sink in for a second. What that means is that if you write a constructive proof for a theorem, you haven't just proven something is true. You've also written a computer program that is guaranteed to work correctly. The proof is the code is the proof.
And this isn't just a neat theory. This is the actual logic that powers modern software called proof assistants, tools like Coke, Nuprol, and the others you see here. They're used today to write bulletproof, formally verified code for critical systems, like in aerospace or cybersecurity, where a single bug could be catastrophic. So Brouwer's century-old philosophical fight is now making our modern digital world safer. How wild is that?
So, we end up back where we started, with a question. We asked if every statement is true or false. But intuitionism takes us to a much weirder and way more interesting place. If a proof is a program, and a program is just a series of steps for a machine, then what is your computer really doing? Is it discovering some deep, timeless truth out there in the universe, or is it just building it, following a recipe, one step at a time? It's a question that completely blurs the lines between math, logic, and what it even means to think.